We didn't miss much. So back then, like 140,000 years ago, we were worried about being the lion's lunch, right? And losing blood. If he got us, the only way we're going to survive if he doesn't eat us in whole is to not lose blood, right? So losing blood, especially red blood cells, is a major thing of our bodies to do so we don't lose oxygen. So blood clotting is still in the phase where don't lose blood, build up insoluble proteins, let the platelets do their job. So evolution may not have caught up on that one, you know, because we're still clotting. A lot of people have heart disease, pulmonary embolism, strokes, heart attacks, deep vein thrombosis because of this overclotting, and it creates inflammation. So this is one of those situations where maybe we haven't caught up to that, right? And now, again, today we're not worried about, you know, getting eaten by a lion. We're more concerned about is my Uber driver on time to get me to work, or, you know, there was no skim milk at Starbucks. You know, what am I going to do? I can't have those calories, you know, or I got an exam tomorrow, or am I going to be okay with online classes? You worry about all those things, right? So that creates the inflammation and the release of a hormone called cortisol, which is an anti-inflammatory hormone released from your adrenal cortex. And it's completely appropriate when you're exercising, or when a bear is chasing you, and when you're eating your burrito in Central Park, or a coyote. But it's not really appropriate to have that feeling every day. So you psychology majors might want to pipe up on this to see how that affects your limbic system, and how it gives you fear, and how it affects you physically. And I don't know anything about psychology, but I know these psychological effects can affect you biologically. So it's not just in your head, it's in your physiology, your anatomy and physiology. So these feedback mechanisms are, this one I don't like, because that one could create a problem, cardiovascular problem. Now the strength of the contraction, sorry, I don't know if you can see this so good. Make it a little smaller for a second. So the strength of uterine contractions, now when you know the story, you know, Friday night, the sperm meets the egg in the fallopian tube, and then it forms one diploid cell, and it implants in the uterus, and then it gestates there for 9 months, 40 weeks. So at the end of that 9 months, 40 weeks, hopefully the baby's head is down towards the bottom of the uterus, which is called, and the opening of the uterus is called the cervix. So the cervix is going to stretch, and you have receptors that pick up that stretch receptors in the cervix of the uterus. And that's going to send a signal input to the control center, which in this case, again, it happens to be the hypothalamus. And the hypothalamus is going to stimulate the pituitary gland, which is the posterior pituitary gland, to release a hormone that's going to target the effector, which the effector is going to be the muscle walls of the uterus. Anybody know what that hormone is? Begins with an O, ends in a tocin.
Oxytocin.
Oxytocin, right? Oxytocin. So oxytocin targets the uterine walls from the hypothalamus, or really from the posterior pituitary, and that causes contraction to expel the little baby out of that uterus. And that keeps, and as long as that stretch is there, that output of oxytocin is going to keep going and keep going. There's no homeostasis there. It's like, get this baby out, or this fetus out, and get the placenta out on top of it. So it's not going to stop until the stimulus is gone. That's positive feedback. Same thing with breast milk ejection, and that's also oxytocin, actually. Oxytocin, when the newborn suckles the mammary gland or the nipple, the input is sent to the hypothalamus to release more oxytocin back to the mammary glands, which eject the milk based on the suckling. So that'll keep happening. That'll keep happening as long as that stimulus is there. Blood clotting is another one, unfortunately, that as long as there's something irritating the walls of the vessels, it's going to continue to clot. But there are mechanisms in the body which we'll learn that try to slow that down, at least, and try to break up the insoluble clots. Okay? So there's two ways of regulation of these processes. Intrinsically, and this is within the organ itself, like the heart maybe has a couple of the blood vessels, of course, have many intrinsic receptors, and they can send out signals to neighboring cells. And I think this regulation is going to be, we're going to talk more about this in endocrine, which is hormone release, because you could have local hormones released, not to the next cell, not just in the blood to a distant target. Extrinsically, the brain, again, controls everything. So the brain will send a signal to a gland and then use the endocrine system or its own system, like the sympathetic. Remember, we talked about the sympathetic and parasympathetic are part of the autonomic nervous system. And that the two branches are the sympathetic and parasympathetic. Remember, I talk about this a lot. The autonomic nervous system, sympathetic branch is what we call fight or flight, right? And parasympathetic is rest and digest, so rest and repose. So parasympathetic seems to, calm things down and slow things down for the most part, except for digestion, because it's digest. Remember, rest and digest. Whereas sympathetic is more fight or flight, and the blood's going to your brain, and your brain has to think quick. Am I going to fight this coyote in Central Park, or am I going to run away? Fight or flight? Somebody have a question? Everybody okay? So the term innervation is good because the nervous system innervates organs, it innervates tissue, it innervates muscles, glands, the heart. But you're going to see the heart has its own built-in conduction system. So basically the nervous system controls the heart, like for heart rate, heart contractility. Endocrine, let's just get the word down. Endocrine means to secretes its products. So it makes hormones and it secretes directly into blood, into the bloodstream. Like testosterone or estrogen are secreted from the gonads into the blood. Where the word exocrine, again, I talk a lot about neuroendocrine. So exocrine, it secretes sometimes out of the body, like in the sweat gland, or into ducts, like the pancreatic duct for digestive enzymes, and into the oral cavity for salivary enzymes, ducts like that, into the digestive tubes. So exocrine doesn't go into the blood. Like the testes and the ovaries. The testes, they manufacture the sperm and they manufacture the testosterone. Ovaries manufacture estrogen, progesterone, and they manufacture follicles which have oocytes or eggs. So in the male, the sperm is ejaculated out through the ejaculatory duct through the urethra, but the testosterone, of course, is secreted into the blood, not the other way around, just if that helps you. And same thing with estrogen and oocytes. Oocytes are ovulated into the blood. They're ovulated towards the fallopian tube from the ovary. Okay, and the estrogen and progesterone are secreted right into the blood. So it's got to be a lot of blood supply in those places. Okay, this is talking about, this is where we're going to go with nervous system. This is neuroendocrine. So again, the difference from laying down to standing up. Right, and then I like that their book uses this so quick because this is a really important receptor and output here. Let me just see where this is going so I don't go too far. Because again, this is more of an introductory class. So let me ask you this. Try to stay with me on this because this is kind of important. When you're laying down, right, there's no gravity. And this is called supine, laying on your back, face up, supine. So your blood flow to your brain is good, right? Yeah, good blood flow. There's no gravity stopping it. So when you stand up, then now the gravity is going to be bearing down. And just on gravity alone, it's going to be making it hard for the blood to get from the heart through the aortic arch, the carotid artery, to your brain. Everybody with me on this? So your blood pressure, again, is falling because you're laying down, so your blood pressure is low. So if you get up real quick, you're gonna have gravity fighting you. So there's receptors for pressure. What do they call? Anybody remember what they call those receptors? Not thermal. Those are baroreceptors. Very good. So the baroreceptors will now sense the change because you're getting good blood flow laying down. It's banging against those baroreceptors are above your heart. So now when you stand up, there's no blood hitting, or less blood and less pressure hitting those baroreceptors. So now that's the signal from the baroreceptors to the medulla oblongata. And there's a cardioacceleratory center is going to stimulate the sympathetic nervous system and the motor fibers, which you'll learn what that means later, to increase the heart rate and increase blood pressure. And it also does that by affecting the blood vessels too, not just the heart. So what if this didn't happen? What if we had a problem here? There wasn't enough sympathetic stimulation. What's going to happen to this guy that stood up? That's my point.
Get lightheaded?
Yeah, he's going to get what's called syncope. Syncope is a lightheadedness or a dizziness, whatever you want to say. And that means all that happened was the sympathetic nervous system didn't kick in time to get the blood to his brain cells. So he lost, kind of semi-lost consciousness and felt lightheaded and dizzy. That's syncope. So this mechanism has to work. Can't override it where his heart rate goes up so crazy. But you need that release. And there's hormonal release. Now, I might as well bring it up here. But sympathetic nervous system, fight or flight, right? You got it? Fight or flight. So there's chemicals released in the nervous system. And there's hormones released. Does anybody know, like, what the hormone is called, or what the neurotransmitter is called that's released from the sympathetic nervous system? I'll give you a hint. Like, the hormone's basically released from the adrenal gland. It sounds like adrenal gland. Adrenaline, right? Adrenaline is I like to call adrenaline the hormone. And then there's norepinephrine, or epinephrine. It's really they're all basically the same compound. So the sympathetic is going to release these chemicals either as a neurotransmitter, which is called norepinephrine, or by the adrenal gland, adrenal medulla, actually, in the form of adrenaline as a hormone. So the nervous system, norepinephrine, works very quickly and kind of goes away quickly, where the hormone stays around a little bit longer because it's in the blood. So the endocrine system works a little slower and longer than the nervous system, right? Like, and it works the same, let's say, and again, hopefully nobody in this class, and I hate when that happens, but it happens. Like, say somebody's allergic to legumes or somebody's allergic to peanuts, right? And they're exposed to them. What happens to them? What does that call, that shock they go into?
Anaphylactic shock.
Yeah, what does that mean, anaphylactic shock? Anybody know?
Unprotected.
Literally, right? Literally. But what really happens in very good. What happens in anaphylactic shock is that the blood pressure drops way below homeostatic range because of vasodilation. Your blood vessels just vasodilate. And then your blood pressure drops, severe drop in blood pressure. So and if you know you're allergic to peanuts, what are you carrying around?
EpiPen.
Yeah, epinephrine pen, right? An EpiPen, epinephrine pen. So you're basically mimicking the sympathetic nervous system by using that epinephrine, which can work as a neurotransmitter or a hormone, whether it's in the blood. EpiPens don't go right into the blood. It's intramuscular, so it's going to kind of help both. But you get a good dose of epinephrine, and then it's going to raise your blood pressure and your heart rate, and hopefully you'll come out of it, right? Makes sense. So it's kind of the same, except at least inside we have these baroreceptors for minor changes. Of course, that was a dramatic example of, anaphylactic shock, systemic vasodilation, which is a horrible thing. And again, our bodies are really sensitive about that. Number one, because we need the blood go into all the tissues and mostly to the brain. Yeah. So hormones are secreted in response to specific stimuli. I think we got the blood sugar thing down already, but we're going to talk about that a lot when we do endocrine, probably the biggest thing. So insulin takes the glucose, we can stop saying sugar after a while, and it puts glucose into the cells to ultimately get into the, into the cytoplasm, and then be broken down, and the byproducts of glycolysis, which is breaking down glucose, goes into the mitochondria with oxygen, and it makes a whole bunch of ATP. Excuse me. So if you have decreased blood sugar, like hypoglycemia, more likely you're going to have glucagon release, and insulin's inhibited. That's that Shakespearean tragedy, right? Glucagon. These two are like evil cousins, insulin and glucagon, when it comes to blood sugar. Now remember, blood sugar, not sugar in the cells, not glucose in the pancreas. We're talking about in the blood. And it usually involves that agonist and antagonist to keep homeostasis within levels. And it's usually about the blood, like what's going on in the blood. Like I said before, like your body doesn't care how much glucose is in a cell, doesn't care how much calcium is in the bone. The blood is where everything is tested and everything is sensed. That's a good way to put it, right? And sometimes within an organ, sometimes within specific cells, which you'll see. And there's glucagon, talking about the opposite. So here's the difference between the two. So again, this is normal. This is not hyperglycemia versus hypoglycemia, although it can explain that a little bit based on the two hormones, right? Insulin versus glucagon, and which one goes up, which one goes down, right? So we talk about fasting, right? We want to see what's going on with your blood. You don't fast too long, right? You fast, that's why I said like 12 hours maybe for a blood glucose test, because your blood glucose is going to go down, but you want it in homeostatic. So you might get a release of both insulin and glucagon within that 12 hours, but not too much of each, if you can understand that. And the pancreas makes and secretes both glucagon and insulin, and they call it the islets of Langerhans, because the rest of the pancreas is all about exocrine and digestion. So in fact, the pancreas is much more involved in digestive enzymes and exocrine than it is endocrine. This is just big with these two. These are big. So insulin is from the beta cells of the islets of Langerhans, and glucagon is from the alpha cells, if you want to remember that for later. So in this case, you're fasting, and you're going to have less uptake of glucose, and you're going to have more breakdown of stored glucose in the liver, which is that's glycogenolysis, which we'll learn, because we store glucose in the form of glycogen in our liver and skeletal muscle. Again, that's something we're going to go over a lot. I know I'm talking fast about it now, but we can store a certain amount of this carbohydrate. So glucagon is going to stimulate the liver to break down glycogen into glucose to get it back to homeostatic range. And hopefully that'll be happening in the 12 hours that we're fasting for a blood count or a blood test. Now, every time you eat, we go to, especially I used Dairy Queen before because it's just a dramatic increase in blood glucose because it's in our blood. So you're going to get the sensation, well, the sensory really, the sensor is really the pancreas, not the brain. This is the one place where the brain is not the integrating or control center. So the islets of Langerhans, especially the beta cells, will be stimulated to secrete more insulin and take the insulin out of the blood and put it into the cells and then decrease the blood glucose. Not too low, because it's got to be in homeostatic range. So these two systems have to work together as much as it's the Hatfields and the McCoys and the yin and yang. They have to work together to get the right outcome. And that's homeostatic blood glucose levels. because that's how our cells function. We have to have the right amount of glucose, whether we're studying for an exam or we're being chased by a coyote in Central Park, because we're going to need energy for both. Okay, so we'll move on a little bit. Don't go too far today. The primary tissues. We're going to talk about chemistry next time. So this is basically where we went through before, the levels of organization. Remember, this is like the first thing I talked about when we took notes. So below the cell, we have some things you need to know for this class. Of course, you need to know the subatomic particles. You need to know what else? Atoms. Then you need molecules, very good. And organelles. Let's do it all. Why just start at the cell? So this is your first level of organization that we consider living things, though, and that's a key. Like an atom is the smallest thing, or the subatomic particles are even smaller, but an atom is more of a particle, a larger particle, but that's not a living thing like a cell. So that's the basic structure of all living things, the basic unit, I should say, sorry. And then if you put similar cells together, you get tissue, and you memorize the tissue. So let's do those. There's epithelial, what's the other ones? Muscle,
Nervous.
connective tissue, and nervous tissue. Those are your 4 basic tissue types. Okay. Then you put 4 tissue types together, and you could get organs. The heart is an organ. The brain is an organ. Pancreas is an organ. And then if you put multiple organs that help out the function of that system, you have an organ system. I really should say organ system. So like digestive system, there's primary organs of digestion. Like the esophagus is only interested in digestion. The stomach, the small and large intestine are only involved in digestion. But the pancreas we saw as both. It could help with the digestive system and exocrine, and it's also part of the endocrine system. The liver is important in digestion, and the gallbladder is important for digestion. But the liver has multiple functions in other systems. So you have to see how, not only how one organ system works, but how the organ systems work together. And some organs could be part of 2 organ systems, or 3 even. Kidney does a lot. Kidney does a lot. It's endocrine. It's urinary, of course. So we have to look into all, and part of your cardiovascular system in a big way. And you have to be able to explain that by the end of the semester, and you will. So your organ systems together make the organism, and that's where homeostasis keeps everything in check. Really important. So you learn some big things, right? We learned about these molecules like oxygen, carbon dioxide, ATP, proteins, carbohydrates, lipids, and nucleic acids. We'll talk about each of them. Atoms like carbon, hydrogen, oxygen, and nitrogen mostly. And we'll talk about others. And there's ions of those basic atoms or elements. The electron, subatomic particle that likes to party. And the protons and neutrons that give the elements their weight and mass and form isotopes sometimes, which you'll see are different numbers of neutrons within that element. So that's where we're going to go. So the primary tissues, muscle tissue, and there's 3 types of muscle. There's skeletal, and then you have cardiac or heart, and smooth muscle, which is also called visceral. So let me ask you this. Which one of these 3 muscle types is voluntary, where we can control it with our thoughts?
Skeletal.
Yeah. So thank God these two are not. These are involuntary. Cardiac muscle is very specialized. It has its own conduction system. It has automaticity, you're going to see. Relies heavily, both of these two rely heavily on glucose and insulin and oxygen to make ATP for muscle contraction. These not so much. They don't rely on oxygen. These have their own system of using glucose, bringing calcium to their cells and making that contraction happen with the help, of course. And I told you that muscle isn't the brightest muscle in the tissue group, but it needs a stimulation for the nervous system a lot of times. So, but smooth muscle is mostly in your blood vessels, which you're going to see, and visceral means organ. Let me ask you this too while we're here. Which one do you think of these three is the most regenerative if injured, torn, or destroyed?
Smooth.
Yeah, it's smooth. Very good. It's smooth. There's an ability for angiogenesis to make new blood vessels and undergo. And everybody know what mitosis is? That's somatic cellular division and reproduction. So mitosis is more likely in the smooth muscle. Cardiac's the least. You damage the cardiac muscle by ischemia, by lack of oxygen, because we have a coronary artery that's occluded, myocardial infarction, which is death of the tissue. That's irreplaceable, unregenerative. Skeletal muscle, a little bit better than cardiac, but nowhere near as regenerative as smooth muscle. Nervous tissue invites a lot of electric controls everything, right? So we got to talk about ions like sodium, potassium, calcium. Remember, calcium important for muscle contraction and nerve conduction. So these need a lot of blood supply. They need a lot of blood. And they do have a lot of blood. And when you hear the word a lot of blood, it means, well, another word for that is vascular. Where epithelial tissue is avascular, no blood supply. It relies on diffusion, which you're going to learn about in cellular transport. So whenever you see an A in front of something or an AN, it means it's not there. Avascular means no vascularity, so it relies on cell transport with things like diffusion, osmosis, active transport. So epithelial tissue lines things and covers things. And your glands are epithelial tissue, sweat glands, your pancreas, beta cells and alpha cells of your islets of Langerhans. Connective tissue is a little more complicated. And yes, it does have connection and does have a lot of protein, so it's a lot of your structure. But it's also cells with a matrix, like, you know, your tendons, ligaments, but also blood,
Skin.
bone, and adipose is connective tissue. So then that's besides the high collagen structures that connect two things together. Like a ligament connects bone to bone. A tendon connects muscle to bone. And you might hear of a term called fascia or aponeurosis. That connects muscle to muscle. So that's usually a lot of collagen, your ligaments, tendons, and that white tissue that we call fascia that's been between the muscles. So there's particular structures, and they have physiology, or they help with physiology. So the big thing with anatomy and physiology, usually the anatomy is going to mirror the physiology. It's very specific, you know, why your teeth shaped like they are, or why did, you know, these glandular cells have these little straws on them that help secrete things, or why does, you know, in your large intestine you have these microvilli that kind of increase the surface area to absorb vitamins and water and all these things. So, and it's really clear in epithelial tissue. So we'll go through all those. It's a lot of stuff this semester. Yeah, muscle tissue, we talked about the three, and we'll go more into those. It's good that you get a head start on all this stuff. And you told me it was voluntary. And so see, when we do muscles, we'll talk more about it. And skeletal muscle is, and I like to talk about this because skeletal muscle, like every muscle, needs a conduction or needs an impulse from the nervous system. So skeletal muscle tissue is voluntary. Therefore, it deals more with the somatic nervous system. You'll see why later. Like the heart, remember the heart and the glands? That's dealing more with sympathetic and parasympathetic, which is autonomic. So somatic is like the different part of the nervous system. So when we go to the nervous system, we'll talk about that. But this is somatic, voluntary. We're using conscious control from our cerebral cortex, which is our area of thought, decision, and cognition, and volition to voluntarily move a muscle. And we have to get into that and all the physiology between the neurotransmitters and the calcium release and the ATP. There's a lot involved. So the skeletal muscle is moving bones. And don't forget the shivering, right? When we shiver for that feedback mechanism, we're contracting skeletal muscles reflexively, which is really not voluntary. So that can't happen. And your diaphragm skeletal muscle, which we learn a lot about the diaphragm, is skeletal muscle, but it's not always voluntary. Like we can control when we sing, right? You guys are singing, you know how to control your breathing if you're dancing and using your diaphragm. So the diaphragm has unconscious control, right? But it also has some conscious control. So it's really not totally true that it's completely involuntary. So your diaphragm, you can control a bit, but most of it is unconscious. So this helps with breathing, the diaphragm. And of course, you have the esophagus, and sphincters, which are kind of like valves that let certain things in or out of blood vessels, let things in and out of digestive tubes. Your tongue moves reflexively in the digestive system. So this contraction of smooth muscle is called peristalsis. I always like to bring up that term too, but this is more smooth muscle, not skeletal. I mean, you have conscious control of these things. You can move your tongue. You can move your diaphragm. You have sphincters that are voluntary. Urinary sphincters, large intestine sphincters, or anal sphincters. And you can swallow. You have muscles of swallowing. But you also have other muscles, smooth muscle within there that is involuntary. So these, I think you have to kind of realize that these could be both voluntary and involuntary. And you're going to learn that. So again, you have to know that right now, but it's good to start thinking that way. So more about skeletal muscles, and you'll learn more about this. I'm not teaching skeletal muscle right now because we just get an intro. You're going to hear the word sarcomere. Sarco means muscle. And there's sarcomeres in cardiac muscle too. So, this is kind of a general look. This is histology. We're going to do a lot of histology in these organ systems or the tissues when we do the tissues, especially tissues, because histology means the study of tissue. So you're going to look at skeletal muscle and you're going to see the striations. You're going to see the multinucleated peripheral nuclei. And it's very linear. So you're going to look at histology. Cardiac muscle is only in heart. So cardiac muscle is specialized because it has its own conduction system. So this is not as linear. It's got striations, but if you ever have a test on this and you want to know the difference histologically between skeletal and cardiac muscle, these intercalated disc structures are a hallmark for cardiac muscle. And the nuclei are usually centrally located, only 1 or 2 nuclei per muscle cell. So the intercalated discs are really important because they hold these areas of muscle together, and there's gaps within them that have ions traveling from cell to cell, especially calcium and sodium and potassium. So, but really the big difference, we think about it, like between, well, first of all, voluntary skeletal muscle and involuntary cardiac muscle, which also has nerve. These are this white area is actually cells that are for conduction. So think about the oxygen demand for those. It's very important oxygen demand for both of these. So using skeletal muscle, voluntary muscle, if you go outside and you want to, run 1,500 meters, your legs will get tired and you'll use all the oxygen and glucose, build up lactic acid from the metabolism of the skeletal muscle, and the oxygen kind of gets depleted and you get sore. But if you sit down for a while, elevate your legs and stretch out a little bit, you're going to get that oxygen repaid. So using skeletal muscle is like using a credit card where you could buy now and pay later as far as oxygen debt. But cardiac muscle, this has to beat from the time you're an embryo, like 5 or 6 weeks into gestation. It has to beat every 75 times a minute on the average, whatever it is, for your whole life till you're dead. And that's cash only, right? You need that oxygen, you need glucose, you need insulin, you need to make ATP, and you need calcium in order for this muscle to contract over and over and over billions of times. So that's a big difference physiologically. Anatomically, histologically, it's easy. Okay, this is intercalated disc, this is branching, not linear, it's striated, and it's only singular nucleated. So you have to know all those kind of things. Smooth muscle lacks striations. Of course, it's involuntary, usually a little spindle shape. So where we're going to live with smooth muscle, of course, is in the walls of the arteries and veins and the walls of the organs, or the tubes, really, like the esophagus, the small intestine, the large intestine, the reproductive organs too. So we'll look through all of that. And the nerve tissue. So we'll finish up the tissue types and go through all that, and we'll get into chemistry next time. So somebody remember, it's going to be a whole week since we were here last time. So we'll go through all the tissues and finish that up, right? Anybody have any questions?